All right, Mr. Lawon, let's do part A. So I'm gonna draw my graph. Okay, this is F, this is plus A, this is negative A. Well, to draw like the slope, I'm gonna write Hooke's law, which is F is equal to negative KA. And A is just the same thing as X, but A is like the maximum amount. So I'm gonna isolate for K now. So I have F over A is equal to negative K. And this works because we have F as our Y and then A for our X. And we see that if I have a negative A, then the negative signs will cancel out. So I'll have something really high up here. And if I have a positive A, then there's still going to be a negative. So I'm going to have a negative right here. And this is just going to be a simple linear slope right down the center. Just like that. All right, let's do part B. So I'm going to draw the XT graph. So this is ranging from 2t. And the initial starts at negative A. So let me write A real quick. And then this is xt. So it starts at negative A. And then it goes to equilibrium. And then it goes to A. And I know that each t goes from head to head. So it goes from here to here again. So it makes a full cycle. So I can draw, like that. And then it should be the same thing for 2t. Like that. All right, now for our VT graph, I'm gonna draw another. Oh wow, that's kind of slanted. It's all right. 2t, t, and this time it's not negative A or positive A, it's negative A omega. Wow, that was nice. All right, so we see here that at the bottom, or at the start, the slope is increasing, and the slope for xt means the velocity. So because xt is increasing, vt starts off as positive. And at around t half, we see that xt reaches its peak. So when the spring goes to the peak, v is 0. So around right here and right here, v is going to be 0. So I'm gonna draw like that. And then it's gonna go like this. And then it's gonna match again. Just like that. Okay, I messed up the previous attempt, but our AT graph is going to be basically the opposite of our XT graph. But this time we have negative A omega squared and A omega squared. So we're gonna start off right here. We're gonna reach the amplitude this time. Alright, so for part C, I know that this spring system has no rough surface, so the energy is conserved. So I can just write the statement that 1/2 mv max squared is equal to 1/2 k a squared for the maximum distance. And then I'm gonna cancel out the 1/2, and I'm gonna isolate for v. All right, so I have v squared max is equal to k a squared over m. And then I'm going to square root this, so I have v max is equal to k a squared over m, like this, right? But then the a squared, well, that's ugly. The a squared, square root of anything squared is just that. It's just itself. So I have a and then rad k over m, right? But this student now is talking about wanting to double the amplitude. So V max, and I'm gonna write parentheses nu, is now 2a rad k over m, and then k, this equation is the same thing as V max, right? So V max nu is just 2 V max. So the student is actually right. All right, so for part D, this student is talking about the frequency now. And if we remember that T is equal to 2 pi rad m over k, and then F, or frequency, is literally just 1 over T, then this is, for to be frequency, we literally just have to flip it over. So F is equal to 1 over 2 pi, and then rad k over m. Now, you'll see that nowhere in this problem has the variable a. So this student is wrong, because F is actually not dependent on the amplitude at all, but is only dependent on k and n. All right, for part F, I'm gonna write the equation that I'm trying to derive first, so I just know what I'm gonna look at, All right, so in the spring system, it has no rough surface, so it's conserved. So the energy is conserved. So I can write that E total, which is 1/2 K, Ka squared, is equal to 1/2 Kx squared plus 1/2 mv squared, right? I'm gonna cancel out all the halves. So I'm left with Ka, Ka squared equal to Kx squared plus mv squared. And so these two have like terms, so I'm gonna move this over here. So I have Ka squared minus Kx squared equal mv squared, and I'm gonna factor out the k. This. And I'm gonna square root it. Oh, actually, I'm gonna divide it by m first. That's smart. So I'm just left with v squared. And then after that, I'm gonna square root it. Equal to, all right, so we got here, but we're not done yet. We can factor out the rad k over m. I kind of ran out of room, so I'm gonna just write over here. So rad k over m multiplied by rad a squared minus x squared equal to v. Now, why did I factor out the rad k over m? Well, v max is equal to positive or negative a omega. This derives from this right here, because sine just fluctuates between 1 to -1. So what really matters is just a omega, right? And then v max, as we derived earlier, is also just positive or negative a rad k over m right here. So if we set these equal to each other, like so, we can cancel out the a's. So w, or omega, is really just k over m. And we could plug this in, so omega multiplied by rad a squared minus x squared is equal to positive or negative v, because it can go up positive or down negative, just like this. And you'll see that this matches this. I'm gonna box it for you, Mr. Luong, because I know my work is really messy. Just like that. Wait. All of this was for part E. This is part E. Okay? This is not part F. Part F is the next part. Alright, for part F, I'm gonna first do the label of the box going toward equilibrium. So I have the dot right here, and this is FG, and this is FN. It should be about the same. And right here we have the spring force, because you'll see that this diagram is getting compressed. So when it's getting compressed, this string wants to push it back out. So that's why the spring force is going to the right. But the surface is also rough. So there's some force that's gonna hold it back behind. FK. So now I'm gonna do the labeling away from the equilibrium this time. So this is my dot, and I still have F of G. I still have F of N. But this time, because it's away, the spring force wants to push it back this time because it's stretched out. So it's just like shh, and it wants to go back. So the spring force is now to the left. But you'll see that the box hasn't approached the amplitude yet. So it's still moving to the right. That means that there's still going to be FK, because the block is not at rest yet. All right, for part G, I'm gonna draw the graph real quick. And then this is X, this is 2A, this is negative 2A, this is negative A, this is A. Then I'm gonna label the blue as scenario 1. And then the red is scenario 2. All right, so scenario 2 starts at negative 2A, and then for a period, it should return back. So around half, it should reach the amplitude right here. So it's gonna be around like that, and then so it's gonna continue on right here as well. So it's gonna be the same. Wow. Now scenario 1 is literally just the same, except that it has a different amplitude. So it's gonna be right here. It's still gonna have the same T period. So it's gonna be marked at all these points right here. So you can see that the only thing that's changed is just the amplitude, but the T period is literally the same. They align right on top of each other. All right, for part H, Tm is equal to 2 pi rad m over k, but this one now has 3m. So what's really changed is just the mass. So I'm gonna write T3m is 2 pi rad 3m over k. So now the ratio of T3m over Tm is 2 pi rad 3m over k over 2 pi rad m over k. And then you'll see that this cancels out, and then m, k will cancel out, and the only thing that's left missing, or left remaining, I mean, is just rad 3. Okay, for part I, I'm just gonna show you my math first, and then I'm gonna write my paragraph. So it says right here that they stick to each other, so this is an inelastic collision. So I'm gonna write m and then vm plus 2m, and it's not moving, so 0, and the total mass is 3m, and then v3m right here. And then I'm gonna isolate for v3m, so I'm gonna divide it over. So m times vm over 3m is equal to v3m, and you'll see that the m's cancel out, so v3m is really equal to vm over 3, right? All right, you'll see here that the floor is smooth, and 2m dropped on m at 0, so there's no potential spring energy, and the energy is conserved as well. So we can write 1/2 mv squared is equal to 1/2 ka squared. And then I'm gonna plug in those variables as 3m and v3m squared is equal to 1/2 k a3m squared, right? We're gonna cancel out the 1/2s, and then we're gonna isolate for a3m. So I have 3m v3m squared over k, square root that, equals a. And then you see that the v has a squared, so it's just we can just bring it on the outside. So v3m times 3m over k is equal to a, 3m. Now v3m we found earlier is just vm over 3, so I'm gonna write over here that vm over 3 and 3m over k is equal to a3m. Well, vm over 3, okay, now here v can be written as am rad k over m over 3 and multiplied by rad 3m over k over 1. You'll see that this cancels out, and I'm gonna set this equal to a3m. I forgot. So then really your am is rad 3 over 3. And then if you want, we can like spread it out so it looks more easy to look at. Now rad 3 is around like 1.7 ish, and am divided by 3 already means that it's smaller, so we can really just conclude that a3m is smaller or less than am. Alright, now I'm about to write the best paragraph that you'll ever read in your life. When block m passes through is moving at its maximum velocity VCM. Oh no, not VCM. VM, there we go, correct variables this time, equals a m rad k over m. At this point, block 2m is dropped from rest and sticks to it in a perfect inelastic, oh my god, elastic collision. Applying this conservation of momentum, the new velocity of the combined system becomes v3m equals vm over 3. Since the, oh my god, my handwriting is so ugly. Since the collision occurs at x equals 0, where all the mechanical energy how do I say this? Oh, where all the mechanical energy is just kinetic, the velocity determines the new amplitude. Even though the mass was tripled, the velocity was cut off by a factor of 3, reducing kinetic energy by a factor of 9, because velocity is squared in the equation. 1/2 mv squared. The energy that is lost from the oh my gosh, collision outweighs the effects of the added mass 3m, making the system oscillate. Whoa, dude, I cannot spell today. Oscillate with a small amplitude. Then block M alone, reinforcing that A3M is less than or lesser than AM. Alright, this is for you to read it. I'm gonna read it to you though. When block M passes through equilibrium, it is moving at its maximum velocity. Vm equals AM rad k over m. At this point, block 2M is dropped from rest and sticks to it in a perfectly inelastic collision. Applying this conservation of momentum, the new velocity of the combined system becomes V3M equals Vm over 3. Since the collision occurs at x equals 0, where all the mechanical energy is just kinetic, the velocity determines the new amplitude. Even though the mass was tripled, the velocity was cut off by a factor of 3, reducing kinetic energy by a factor of 9, because velocity is squared in the equation of 1/2 mv squared. The energy that is lost from the inelastic collision outweighs the effects of the added mass 3m, making the system oscillate with a smaller amplitude than block M alone, reinforcing that A3m is lesser than AM.